Okay, hello everybody. You listen me? You hear me?
We do.
Yeah. Today we solve some examples. I hope you see this PDF. Yeah, you see my presentation.
Yeah,
Yes,
we
I can
do.
see it.
Okay. Okay. Today we make something with calculation of Lipschitz constant and Lipschitz condition, local and global Lipschitz. And I will start with example from Khalil book. You can find this example on page uh, on page on page 16. Yeah, and here we have a function f. This function, and its function is continuously differentiable on R2, and it is locally Lipschitz on R2, because when we calculate Jacobian, then we see that this is not uniform bounded, because d if 1 dx2 and d if 2 dx2 is depend on the x, and then it's not uniform bounded. But on any compact subset of R2, f is Lipschitz, and suppose that we are interested in calculating a Lipschitz constant, or the constant set W, x in R, and x1, absolute value of x1 less than a1, and absolute value of x2 less or equal to a2. And the Jacobian matrix is given by the next. Yeah, and using the norm in R2 and induced matrix norm for matrix, we have that maximum width -1 plus x2 plus x1, and x2 absolute value of x2 plus absolute value of 1 minus x1, and all points in W satisfy that -1 plus x2 plus x1 less or equal to 1 plus a2 plus a1, and x2, the second part, x2 absolute value of x2 plus absolute value of 1 minus x1 less or equal to a2 plus 1 plus a1, and therefore the Lipschitz constant can be taken as L equal to 1 plus a1 plus a2. Okay, the next example is a predator and prey model. x1 dot equal to a x1 minus bx1 x2, and x2 dot equal to c x1 x2 minus d x2. Here a, b, c, d is a positive constant, and x1 and x2 greater than 0, because x1 is a predator and x2 is a prey. Okay, and here the equilibrium points are 0, 0 and 1, 0. And if we calculate the Jacobian, we can say that it is local Lipschitz on R2, and I can show you the sum simulation in MATLAB now. Okay. Sorry, I try to, yes, here, yes. Okay, and now you can see this figure from simulation. Here, one equilibrium point 0, 0. It is a saddle point, and another one, 1, 1 is a center. And you can see that this vector field is show how this model working, yeah, and we can try to start with different initial condition, and now I try to change my code. Okay, and now you can see if we start with different initial condition, 0 point, which is, I think, this 0.5, 1, 1.5, 2, 2.5, and 3. You can see that the trajectory always bounded. Yes. Can you do you have any question here with this model? Okay. And we can see that all this trajectory bounded, and
so if I may have comment, the lecturer. So this example is example for use of these lemma. I explained just this GULL. So if you look at Jacobian on the whole Rn cannot be bounded. So you cannot say that it is global Lipschitz. System is not global Lipschitz, but because of this property which is now shown, we know that trajectories are bounded, as later illustrated also by MATLAB code. So we know that we may use the lemma that even local Lipschitz property is sufficient to conclude that solution exists for all times, because we do not have any kind of escape to infinity. All curves are closed and solution bounded. So we cannot use the second lemma which says that if right hand side is global Lipschitz, then we don't have finite time escape and we have a unique solution existing for all times. But we may use this later lemma that if we prove in somehow different way that trajectories are bounded, that we are not obliged to check on the whole space that Lipschitz constant is bounded, which cannot be true here because of these terms x1, x2. It's clear that Lipschitz constant on whole Rn will not be bounded, so system is not global Lipschitz. So that's my comment.
Okay, thank you. Okay, we can another we can found the function v with the next step. Yeah, like on presentation in lecture. We can separate this and then we integrate and take exponential, yeah, and can found this constant C2, yeah, and we can see that constant C2, this value is of this integral is of initial condition is stays the same, yeah, and this bounded. Okay, the next example is the x1 dot equal to minus x2 cubed and x2 dot equal to x1 cubed, and we can calculate the Jacobian, yeah, and it is continuously differentiable on R2 and it is local Lipschitz on R2, but it is not global Lipschitz since the Jacobian is not uniformly bounded on R2, and we can found in the same way the function, the next function v, which is a constant along trajectory of solution, and therefore trajectory are bounded. The same. This example is like previous example of predator and prey, the same results. This system is not globally bounded, but it's not escape to infinite time and has solution. And the next example, x1 dot equal to minus x2 in 1 divided 3 and x2 dot equal to x1 power to 1 divided 3, and function phi is discontinuous of R2. Right hand side is not local Lipschitz in 0, 0, and has it's not local Lipschitz on R2.
Sorry, function is continuous, but it doesn't have derivative at the origin, but it is continuous.
Yeah, sorry, it is continuous. This is a mistake. It is continuous, but I make copy from another slide maybe and make this mistake. Yeah, but and we can found a function v which is constant along the solution, and this function grown to infinity when x grown to infinity, and therefore it cannot expand to infinite time. And v is 0 only at the origin. Out the origin, it always greater than 0. And therefore, any trajectory starts out of origin can get to the origin, which is not local Lipschitz. And unique solution exists.
So if I may have comment,
yes.
So this example shows this very basic theorem on local existence. Is really very rough one, because you see that at the origin system is not smooth, system is not locally Lipschitz. Even at the origin you may easily check, because derivative is unbounded and at the origin doesn't exist. Yet we can see that solution exists, is unique for any initial condition, and even can be prolonged on unbounded time interval. So no and that's because also this reason is that, okay, this function v equal to x1 4/3 and plus x2 4/3. Obviously, if x1, x2 go to infinity, this function goes to infinity, right? But we can show by taking derivative that this constant this function w is constant along trajectory, which is not shown on this slide. And then it is contradiction. So because the function is constant, trajectory cannot escape to infinity, because if trajectory escape to infinity, then also this function W escape to infinity. Sorry, no W escape to infinity. And it is not possible because we see that it is constant along solution. That excludes escape to infinity. And of course, at the origin, we don't know, but we can conclude another thing. You can see that if this function v is constant, that it stays away of the origin. So any solution which starts away of the origin stays away from the origin at least some distance. Therefore, at the origin, there is only one solution, which is equilibrium solution. So there is not this case like in some simpler example in lectures, like x dot equal cubic root of x, which allow two solution here. Even if you have the same cubic root, the solution is always unique and exists, and system behaves perfect way. So this is good to remember, because in some tests or examples, sometimes students tend to see this system and say, okay, there is this cubic root, and I remember with this cubic root, there is no unique solution. No, it's just sufficient condition, this Lipschitz condition. So this examples is meant to serve, like, show you that even with very bad looking right hand side, you still may have unique solution for every initial condition existing for all times, and everything is perfect. Okay, thank you.
Okay, thank you. And the next example is a function f from x is equal to this, equals the next x1 dot equal to x2, x2 dot equal to minus saturation x1 plus x2, and it is not continuously differentiable on R2. Let's you check its Lipschitz property by examining fx minus fy using non-PFO vectors in R2, and the fact that the saturation function satisfy the next inequality, and then we obtain that is less than or equal to x2 minus epsilon2 squared plus x1 plus x2 minus epsilon1 minus epsilon2 squared, and this less or equal to x1 minus x1 squared plus 2x1 minus x1 times x2 minus epsilon2 plus 2 x2 minus epsilon2 squared. Here we only separate this like a and b, this x1 minus this term epsilon1, and this x2 minus epsilon2, yeah, and then we can use do you have any question here in this step? Okay, and then we're using the inequality a squared plus 2ab plus 2b2, here 2b2, and this equal to the next vector transpose this matrix P and the vector AB. This is less or equal to lambda max from this matrix P, of this matrix P, and times norm AB. Yeah, and we conclude that if the norm fx minus f epsilon less or equal to square of 2.3 618. This is a maximal eigenvalue of this matrix. Yeah, and and norm x minus epsilon 2 for all x epsilon in R2. And here we have used a property of positive semi-definite symmetric matrix that x transpose times p x less or equal to lambda max, maximal eigenvalue of matrix P, and times x transpose x for all x in Rn. Okay, and
Volodymyr?
Okay, yes.
Are you sure there is square root of this? Maybe there is already this 2.68 without square root? No. Oh.
Sorry.
No. Okay. Lambda max is this, yeah?
Yeah.
Square root because you take square root of this. Okay. I agree.
Okay, and the result of this calculation is that Lipschitz constant L equal to this square root 2.618. Okay, and next slide. Next example is from exercise from Khalil book, and function phi is a pendulum. Function phi is given by the next equation. X1 dot equal to x2, x2 dot equal to minus sinus x1 minus bx2 plus cu is continuously differentiable on R2, hence it is locally Lipschitz on R2 because we can calculate a Jacobian, and when we calculate a Jacobian, we can see that all derivatives are uniformly bounded of R2, and therefore this system is globally Lipschitz. This function. Any question here? Okay, the next example is mass spring system. X1 dot equal to x2, x2 dot equal to minus kx1 minus cx2 minus function eta depend on x2 x2 and plus u and divide to m, and function eta is discontinuous on R2, and hence it is not locally Lipschitz on R2, but eta is continuous and continuously differentiable on the next, on the D1 R minus infinity 0, and function f in C1 on D1, and therefore function f is locally Lipschitz on D1. In the similar way, we can found that function phi is locally Lipschitz on the next three domain. Okay, the next example is a
maybe come back to this example.
Yeah.
I may comment.
Because
one slide back, yeah. Okay. So this example is like first example in Khalil book in this appendix, and it is nicely explained what this term eta x1 x2 means. These are various models for more complex friction in the system. Yeah, so obviously kx1 is viscous friction, but then you may have dry friction, column friction, static friction. There are various models, and often, of course, for instance, in case of dry friction, sorry, not dry friction, static friction, Coulomb friction, this is discontinuous. So this means that for some velocity, then it's stop and then it suddenly moves. So in this case, it's I think maybe better to read everything in the book because it is explained, and it may happen that there are more than one solutions and so on due to this friction. But if you of course remove this term eta, then everything else is very simple and Lipschitz and everything exists. So this is just maybe my comment to it. This is a little bit long and complicated example. Yeah, this is example when you have some mass which is lying on some surface and you are pulling it using some spring, and you can imagine that there may be strange behavior, like you are pulling the spring and nothing happens, and then with certain force suddenly mass is moved because it overcomes dry friction. Meanwhile, spring is stretched, so mass moves, but then it moves quicker that you are stretching, for instance, spring. So when spring is becoming less stretched, then suddenly force is again small and mass again stuck on one place and doesn't move. Yeah, so this is very interesting situation, and you may also find in this example some basic types of friction model listed, which is useful because friction is really in many systems most peculiar things. So I suggest you to read this example very well in Khalil book. Thank you.
Okay, thank you. And the next example is tunnel diode circuit. We saw this example on previous classes, yeah, and function phi is given by the next equation, x1 dot equal to function minus x1 plus x2 divide c, and minus x1 minus r x2 plus u divide l, where cl is greater than 0, yeah, and suppose that function I is given by the next, yeah, and let's calculate the Jacobian, and all derivatives in Jacobian are constant function, continuous and bounded, yeah, these three except this first partial derivation of phi1 to x1, which depend on derivation of x1, and from this we can see that derivation of x1 is depend of here, for example, x1, x2 squared, x1 cubed, x1 squared, and cos1 cubed, and so on, and it is not bounded, and therefore this function is locally but not globally Lipschitz. Okay, the next example is the one-dipole oscillator. This example is okay, you can find this in appendix in Khalil book, page number 348, and here function f is given by the next function f is given by z1 dot equal to z2 divide eta, and z2 dot equal to the next, and L C greater than 0, and this term is equal to square root of L divided C, and let's calculate the Jacobian. and function, and we can see that this function is local Lipschitz on R2, and partial derivation are not bounded on R2, and therefore function f is only locally Lipschitz on R2, not globally. Yeah, because this term z2 squared here. Because the next exercise is DC to DC power converter. Function f is given by the next equation, x1 dot equal to minus 1 divide k x2 plus x2 plus k times u, and 1 divide k x2 dot equal to 1 divide k x1 and minus alpha x2 minus x1 plus alpha k squared times all this term times u, and we calculate the Jacobian and suppose that u continuous function of time, k is greater than 1, and then all derivatives are continuous, and therefore f is local Lipschitz on R2. As we know, u is bounded, and if u bounded on R2, then f is globally Lipschitz. Do you have any question here? Okay. The next examples, biochemical reactor, and function f is given by the next equation. x1 dot equal to x1 times nu function nu from x2 minus u, and x2 dot equal to minus alpha minus 1 x1. This function nu depend on x2, and plus alpha minus x2 times u, and suppose that function nu is given by the next equation. Yeah, and let's calculate the Jacobian. And we see that Jacobian is depend on derivation of function nu, and yeah, here is Jacobian. Here is the derivation of this function, and since nu from x2 and nu and derivation of nu of x2 are discontinuous on R, function f is not local Lipschitz on Rn. Function not mu but nu, function nu, this is a mistake, sorry. Function nu from x2 and derivation of nu are piecewise continuous, is continuous on R except this point, and at least this term is unbounded. Therefore, the function f is only locally Lipschitz. Do you have any question in this example? Okay. The next example is the DC motor when Fe and Fl are linear function. Function f is given by the next equation, this matrix this and this matrix, and let's calculate the Jacobian of this. Yeah, and we can find all partial derivation are continuous, and therefore f is local Lipschitz on R3, but this one, and this one, it's not bounded on R3, and therefore is not globally Lipschitz. Any question here? Okay. The next example is the electrostatic actuator function f is given by the next equation. Yeah. And by definition, x1 is constrained and greater or equal to x1 is greater or equal to 0 and less or equal to 1 minus sigma. And let's calculate the Jacobian. And all partial derivation are continuous. Therefore, f is locally Lipschitz on R3, but these three terms are not bounded on R3, and therefore f is not globally Lipschitz. Okay. And now I open another PDF file. Oh, okay, and now we have some time, and we can each student can calculate this example, and you need to check if these systems locally or globally Lipschitz, if the solution is defined for all t greater or equal to 0, it means that this system can escape to infinity time or not. Yeah. And I give you some time now, and maybe someone from you know if this system is globally or local Lipschitz. You hear me?
Yes, I can hear you.
Okay. Can you check if?
I would say it's globally Lipschitz.
Why?
Because it's of the cosinus and sinus, it's bounded. And it's also continuous.
And do you calculate Jacobian or not? You need to calculate Jacobian. Okay, it's true. This first system is global Lipschitz because you can calculate Jacobian, and then Jacobian is equal to first term is 0, then 1, 0, and some term depends on x2 and on cosinus and sinus x2, and this function is bounded, and then we can say that f is global Lipschitz. Yeah. And therefore it does not escape to infinite time. Can you check this second or this third, for example? Maybe someone can say something about this third example.
The third should be global Lipschitz because it has constant Jacobian.
Yes, because this system is linear time invariant, and Jacobian is equal to 0, 1, 1, 0, and LTE systems do not escape to infinite time. Yeah. And the second one, any ideas here?
I'm still calculating the Jacobian.
Okay.
But I would say it's also globally Lipschitz because the Jacobian is, yeah, 3 elements are zeros and ones, and one element is, if you derivate the first term after x2, then it will get x over 4, and so this is bounded, and so it's globally Lipschitz.
Mm-hmm. Okay. Maybe someone.
No, it's I guess it's not continuous. So
Why it's not continuous? It's continuous. No? Because here, okay, it's always positive.
okay.
Yeah?
Yeah.
It's okay.
Is it bounded because the term will be increasing for larger and larger values of x, I think.
Okay, you can calculate the Jacobian, and then first term, for example, here I show you. I think this first term is 0. The second term is x2 power 4, and times 5 plus x2 power 4, and divide to 1 plus x2 1 plus x2 powered 4, and this term squared, yeah. And if you found limit, yeah, calculate limit when x go to infinity in this term, yeah, then this limit equal to 1, yeah, and here it's 1 and 0, yeah, it's this 1 and 0, yeah, and 0 and this term when you found this derivation, yeah, and then you can find the limit when x go to infinity, and this limit equal to 1, and it is bounded, yeah. And you can show when you calculate this limit, you can show that if limit go to equal to 1 when x go to infinity, that this Jacobian is bounded, and hence this system is global Lipschitz, yeah, and therefore it does not escape to infinity in finite time. Okay. Do you have some question about the material? I put some material from seminar, from the first seminar to web, to Moodle, and you can check. And if you have some question about the calculation of equilibrium points, or okay, today I give you some homework, yeah, and if you open the Khalil book on page 26, I think someone has this book, yeah, this book, and I give you some you need to calculate and solve 1.12, yeah, this exercise 1.12 on page 26, and the last five systems. You, for each of the following system, investigate local and global Lipschitz properties. Assume that input variables are continuous functions of time. Yeah, this R, E, G, K, L. This is the magnetic levitation system, the electrostatic actuator, the two-link robot manipulator, the inverted pendulum on a cart, and the Tora system. And these five, and then I give you as I think that's all. Yeah. Only these five you need to solve. Do you have a question about homework?
Can you write it
To Moodle?
Yeah, thank you.
Yeah. Okay, I put it to Moodle, and I don't know if you have this book, Khalil book, and can. Well, I need to, because all of you have this book or not? Yeah. Okay.
Could you take a photo maybe of the?
Okay. I can make a photo, and I can give a photo of these examples. Yeah. Only write me a mail, and I sent you this material. Yeah.
Would it be possible to put it here on the
Moodle?
Or
On
Moodle?
Teams?
It doesn't matter. Either.
Okay, I ask Professor Chelikovsky if I can, yeah, because I don't know if I can make.
Okay, if I can say, I have PDF with copies of this appendix with examples, and it has some 6 megabytes, and maybe I'm not sure if putting it on web is correct from all these point of view. So maybe sending by email is better. Yeah, so if it is not a problem for you.
Of course.
Because I'm not sure if I can copy parts of the book and put it on internet. Yes. So in library there we bought like 10 or 15 copies for libraries. So we really paid a lot, like department for it. So we are not like pirates, but anyway. Who knows what are the rules and so on. Yeah. So maybe if we send it by email, it would be safer. Yeah.
Okay, thank you.
Okay. Thank you, Sergey. Okay, I put to Moodle this this exercise, yeah, and write you, and maybe I add something to, maybe you can calculate some equilibrium points and apply the first Lyapunov method on several systems. Yeah, for example, I put to Moodle materials with this indirect Lyapunov method, and at the end of this material you can find three systems, yeah, three examples, and you can solve it. Yeah, you can apply this first Lyapunov method and then say if this equilibrium points stable or not. Yeah, it will be a part of homework. Yeah, these five systems, investigate local and global Lipschitz properties of them. Yeah, and the second part is only this small, only found equilibrium points, and apply first Lyapunov method and say if it's stable or unstable or something like we do on our classes. Yeah. Okay. Do you have any question?
Yes, sorry. When it is the deadline for this homework?
I think 1 week. It's okay.
Yes, and we should send it to you by email, like we write it and scan it.
No. You can send me via Moodle. Yeah.
Okay.
I put this homework to Moodle and write about this. And you can go to Moodle and put this homework. Yeah. Via Moodle.
Okay. Thank you.
Okay. Any question?
Sorry, one question. You've mentioned indirect Lyapunov method.
Yeah.
I believe we didn't have it on the lecture yet, but maybe I'm not right.
Yeah.
I believe it's the same thing that we were discussing in the first.
Yes, it's the same. It's the same. Yeah.
So basically, linearization around some.
Yes.
Okay.
It's not so difficult. You don't need. I think you can do it with this material from Moodle. Yeah, because many examples. I don't know, maybe 20 examples on Moodle about the organization.
If I understand which method do you mean?
Yeah, only this first Lyapunov method, this organization. Yeah.
Okay.
Okay, some question? Okay, thank you for your attention. Okay, thank you. Question?
No.
Okay, I think we can finish for today. Yeah. And if you have any question, you can send me a mail, and I put this exercise from today to Moodle, and you can check when you solve this when you will solve this homework. You can you can see how I do it. Yeah, here. Yeah. Okay. Thank you. Goodbye, and see you next week.
Goodbye. Thank you.